Hello there, it's Keith here, and this is lesson 3 of the SuckShoot series of my 6809 assembly programming tutorials. Today we're looking at the FM7 port. The FM7, if you don't know it, is the Japanese 6809 based computer. So you can see the game running here, the same as it did on the Dragon and the Vectrex basically. We have to shoot our flying bats as they get towards the screen, and when they get to the front of the screen they will bite us and we will die, we will lose a life, and we run out of lives, we die. So a very simple game, not really here to show the game as such. We're here to look at the code that makes up the game, and that's what we're going to do today. Now the tricky thing about the FM7 is that unlike the Dragon, the screen is handled by a sub CPU, and so we can't directly access the video memory from our main CPU. And what we're going to do is we're going to send commands to the sub CPU telling it what bitmaps we want to draw and where, and that will do the graphics on this system. Now if you want to see the full details of the FM7 graphics, I've covered them before in the simple series, and also I did some specific breakdown of all of the commands on the FM7 for different graphical effects. So today we're not going to cover how to send commands to the sub CPU. You have to do waits and sends and checks and things like that. We're not going to cover those because they're quite long, and I've covered them in those other tutorials. So today we're just going to look at a basic example that uses those to get the graphics this game needed onto the screen. So either take a look at the code, figure out how it works yourself, or please see those other tutorials if you need a little bit of help. Anyway, let's go over to the source code and let's take a look. Okay, so here's our source code. Now this was ported from the Dragon version. So it's been bits of code swapped in and swapped out because obviously we needed to change the joystick reading routines. We needed to change the graphics routines. It's using Chibi sound for its sound effects, so that was already written, so not much work there. Most of the code is the same though, so we're going to scan through it quickly. So the first thing we're doing here is we're selecting which of the joysticks we're going to read in from, and we're reading in from joystick 1. So we're sending the command to select that joystick to the FM chip. Now the joystick on the FM7 was connected to an FM add-on board, and it's a bit like the AY sound chip. We have to select registers, and there's a data port on that sound chip, so that's what we're using there. We're then resetting the score here, high score, setting that to 0. This is the title screen routine. We clear the screen, wait for fire button to be released. That's because we might be doing a game over. And then we stop all the sounds that are currently playing. And then what we're going to do is we're going to show some strings to the screen. So we're doing a locate and print string here, doing another one here. The text strings are being printed by the firmware, unlike the Dragon where I was using my own bitmap font. This time I'm not. I'm letting the firmware do that because why not? Basically, we can't get directly to the video memory on this system anyway, so we're going to have to send some kind of command to the firmware. So we might as well get it to do its text. So we're just going through here, showing everything onto the screen. We're showing the high score here, and then we're going to show the sprite onto the screen of the bat that flaps its mouth on the title screen. I can just get the title screen back up. There it is. There's that flappy bat. So we've got the position of the bat, and this is effectively the screen center. Now the screen is actually 640 pixels wide, but I'm only using a single byte for the x-axis, so I'm quadrupling it. So 80 will be effectively 320 on the x-axis there, so that's why I'm using that value there. We're setting the scale, that's the z-axis basically, how close the bat is to the player, and that also affects which sprite is being used. And the sprite frame of animation is set to 0 here. And so what we're doing here on the title screen is we are basically flipping the sprite for the enemy bat, that does the flapping effect, showing the sprite. We've then got a pause, we then clear the sprite, and then we're reading in from the joystick and we're waiting for fire to be pressed. Well, let's go straight ahead and let's have a look at this concept of the sprites, because I think we might as well see that now while we're discussing it. So the sprite layout is exactly the same as on the Dragon version. We've got 7 sprites. The first one is our player cursor, and then we've got 2 pairs at 3 different sizes of the enemy bat. So that is every single sprite that the game uses. So the biggest one here is 32 by 32, and that's going to be important later. We'll discuss that later on. So those are our sprites. Now if we go down to the bottom of our code here and try and find it. Okay, so here is the lookup table for our sprite data. This is in exactly the same format as the Dragon. So we've got the address of the sprite data, and then we've got the size X and Y in pixels. Now the format of the sprite data on the FM7 is a bit odd compared to the other ones, because it's actually each byte contains 8 pixels, but there's 3-bit planes. So I've divided by 8 and then times by 3. That's a bit irregular to what I usually do, because usually I just specify the number of pixels per byte and the calculation will work it out, but it's actually not going to evenly divide in that way, so that's why I've done it slightly differently here. So then we've got our sprite base, which is just an import from the Sprite editor. So you can see here, this is the binary file exported by Sprite editor. And if you want to know where I got that lookup table of the sprite information, it's on this sprite list. This export info function will export that, but I did have to tweak it because it's designed for normal bitmap screens, not one that uses 3-bit planes per 8-byte line. So it wouldn't quite work with that. A slight change there. Okay, so how do we show our sprites to the screen? Well, the start of the calculations is the same as on the Dragon. So we've got to basically load the pointer to our sprite data here. We get our X and our Y position for the sprite, and then we jump to the show sprite routine, and the show sprite routine will basically do the job of setting up the sprite. Now on the FM7 we have to send a sequence of bytes to the sub CPU, and this is a sort of command sequence here. So this is the correct data for an XOR command, an XOR copy of some data from the main CPU to the sub CPU, and we pass all those blocks of data to the sub CPU. Now the bit we're going to change is this bit here. This is the start X and start Y and end X and end Y. So this is set up here for a 16 by 16 sprite, but that's not what we're actually going to use. We're going to use whatever we need based on the sprite we're sending. So what we're doing here is we're loading the address of the put pos, which is that line, and we're going to patch in the correct X and Y positions here for our sprite, and that's what we're going to do. So we're first loading in our X position here. We're effectively multiplying it by 4 here, and then we are storing that as the starting position. We're then getting the width of our sprite from the source table. We'll have been passed the source table for the sprite info in Y here. So we're going to get that, and we're going to update the 16-bit value here, and then we're storing that 16-bit value to the destination, which is that table that we're going to then send to the hardware. So we've now done the X position, and we do the same for the Y position here. So here we're getting the Y position. We're just getting in the Y position here, and then we're storing that into that command table here. So that will have updated this line here with the new start and end position according to the size of our sprite. And then what we do is we're going to send this to the hardware. Now we need to get the source address of the bitmap data here, and that's being loaded into X, and then we're going to load the number of blocks that we're going to send. Now each time we run this command we can only send up to about 96 bytes. So we're going to send a total of 3 extra blocks after the first initial block. So that's 4 96-byte blocks, which gives us a maximum of 32 by 32 pixels for our sprite. Now there is a sort of limitation of this code. If the sprite is much smaller than that, we're still going to send 4 blocks, which is wasteful. But rather than try and calculate the exact number of blocks, I didn't spend very long on this program, not going to lie. I just sent 4 blocks every time. The sub CPU will ignore the extra blocks if it doesn't need them, so it doesn't cause any harm. It just wastes some processing power. And I was short of time and I wasn't short of processing power, so that's why I didn't optimize this as well as I could have done. So then what we're doing here is we are sending our command definition here, stopping the sub CPU, sending the main command, and then we're sending the sub data, and that is 48 words 96 bytes of our sprite. Now that's our first block, but we've defined 3 extra blocks, and we do those here, and this is a separate kind of command, a continue command, and we just send that data as well. So that's sending all of the sprite data. Now when it comes to the player sprite, it's very simple. We just load in the pointer to the sprite data table here at the X and Y position, and we show that sprite. With the enemy though, we have to calculate the frame of animation here. So we do that based on the current scale and also the current frame of animation. We have to multiply the frame of animation by 4 and the scale by 8. The reason for that is each entry in our lookup table for the sprite information, where is it? is 4 bytes. So that first one's a word, 2 bytes, and then there's 2 bytes after. So it's 4 bytes per entry. So our pointer to the sprite we want to show has to be multiplied by 4. So sprite 0 will be at the start, sprite 1 will be 4 bytes in, and so on. So that's how we're doing that. Now, here is our main game code. So we start by clearing the screen, randomizing the enemy position. We then set the number of lives, reset the score, set the player's starting position, and set the start enemy speed. Enemy gets faster every time you hit them. And then we just show our score to the screen. Okay, here's the main loop. So this is going to check for the sound, and if the sound needs to be stopped, we will send a 0 byte to chibi sound, which stops the sound. That's just so we can change the length of our sound effects. Here we are effectively updating the frame of animation for our enemy sprite. It updates every frame. Then we show the starting position of both sprites. We delay a bit. That's why I wasn't too worried about optimizing the sprite sending code, because we are slowing the games down. And then we remove the sprites and we recalculate everything. And what we do here, this is based on the simple series, is we're getting the current position of the player sprite. We then read in from the joystick, and this version is the same as the dragon. The data it reads in, its output size, so up, down, left and right are going to be in the same position. And then what we're doing here is we're checking the fire 2. That will make the cursor move faster. And then we check down, followed by right, then up, and then left. And we do those in that order because halfway through we're going to negate our speed for the opposite direction. So that's why we're doing them in that order. And each time we're just checking if the current player position is at the edge of the screen. And if it is, we're not going to move. But if it's not, then we're able to move in that direction. And we're effecting an addition here of A to Y with the load effective address command. That is effectively performing Y equals Y plus A here. I obviously wrote this documentation when that was defaulting to 8, but I later changed it so that it was more flexible, and it actually adds A now. If the fire button's pressed, then we are going to make a firing sound. We then check if the player has actually shot the bat, and if they haven't, we're just going to skip over the next code, but if they have, we make the bat hit sound. We increase the enemy speed to give the player more of a challenge next time, because they're obviously doing pretty well. We add some score using the BCD add routine. I covered the BC add and also the random routines in the multi-platform series, so if you need to know how they work, please take a look. And then we update the score. Now, after that, we are updating the player position here, and then we're increasing the position of the bat. This is basically a counter, so that every time this counter rolls over, we move the bat's Z position closer to the player here. And so if we need to, we will now make the bat bigger. And then what we're doing here is we're checking if the player's at the front of the screen, which is at position 64. If they have, then the player has been hurt. So we re-randomize the bat position. We make the hurt sound. We reduce the number of lives. And if the player's lives have reached 0, we're going to show the game over. And then we update the score, because the score also shows the number of lives to the screen. And that's the end of the main loop. So we jump back up and we repeat again. Okay. So here's the update score routine. Very simple. We just show the score in the far left, binary coded decimal, and we show the lives at the far right. We're using binary coded decimal, but it's actually just a single digit anyway. Just for convenience, they're using the same code again. The game over routine is also pretty straightforward. We just wait for fire to be released. We then silence the sound, clear the screen, show the game over message, and then we use BCDCP to compare the score and the high score. Now, if the player's score is higher than the old high score, we're going to tell the player that they've done a good job. So what we do in that case is we're copying the current score to the high score. We've got a function I use called LDIR2 here. This is just to copy some data quickly. And then we are going to show a high score message to the screen, and then we wait for the player to press fire, and we jump back to the title. If they didn't get a high score, it's almost identical. We just show a different message to the screen, and the messages are game over, new high score if they did well, and game over, you suck if they did not. So there we go. The joystick reading routine, it's just reading in from the FM register here. Very straightforward here. I've covered all of this in the platform specific series in the past again. So if you want to see more about using the joystick, you can obviously just use the code here. But if you want to, really go into it yourself and make sure you understand it, then please either play with the code yourself or take a look at that tutorial. Anyway, I hope you've enjoyed this today. As always, if you liked what you saw, please go to the website, download the source code, and you can, as I would say, you can use any part of the source code in your own programs in any way you manage to do so. You're welcome to do that. I'm going to be porting SuckShoot to more systems. I'm working on an 8086 port, so we'll be porting it to DOS and the Windows one, hopefully. So this isn't going anywhere, and I'm going to be doing more tutorials on the FM7 and 6809 in general. So if you liked it, please hit that subscribe button so you see the future episodes. Anyway, whatever you do, I hope you have fun. I hope you have a lot of success with your programming. Thanks for watching today, and goodbye.